So today we are going to continue with dimensions and dimensional analysis. So dimensions are the powers to which the physical quantities must be raised to represent the given physical quantity. The powers to which the fundamental quantities must be raised to represent the physical quantities. In our last class, we talked about categories of physical quantities. Fundamental quantity is one of them. Derived quantity is another, and then we have supplementary quantity. So fundamental quantities, there are 7 in all. There are 7 of them. Time, length, mass, current, temperature, amount of substance, and luminous intensity. So by definition, they are quantities which are distinct in nature that cannot be defined by other quantities, but upon which other physical quantities are derived. Upon which other physical quantities are derived. So that is our fundamental quantities. So coming to dimensional analysis, they are the powers to which these fundamental quantities must be raised to represent the given physical quantity. Must be raised. So if you look at the formula for force, F is equal to MA. M, which is mass, by dimensional formula, is written as capital M. A, which is acceleration, the unit of acceleration is meter per second square. Meter over second square. So if you convert this to dimensional formula, meter L, second, that is time, raised to 2. So that is the formula for force. MLT minus 2. MLT raised to minus 2. MLT raised to minus 2. M for mass, LT raised to minus 2 for acceleration. So this is the dimensional formula for force. Now, what is the dimensions of force? The dimensions of force are the powers to which the fundamental quantities must be raised. So the fundamental quantities here are the MLT, mass, length, and time. The powers to which they must be raised is the dimension. So M is raised to power 1. M is raised to power 1. L is raised to power 1. And T is raised to power minus 2. So it means that the dimensions of force are 1 in mass, 1 in length, and minus 2 in time. 1 in mass, 1 in length, and -2 in time. So that is the dimensions of force. So remember, the power to which the fundamental quantities must be raised to represent the given physical quantity is known as dimensions. So dimensionless quantity. A dimensionless quantity is a physical quantity which has no physical units. It has no physical units. Now, if we represent dimensionless quantity using a dimensional formula, with that in mind that it has no physical unit, we'll have it represented as m raised to 0, l raised to 0, t raised to 0. So remember, whatever that is raised to 0 is equal to 1. So if we apply that rule, m raised to 0 is 1, l raised to 0 is 1, t raised to 0 is 1. So these together shows that a dimensionless unit physically has no units, or we can say that the unit is equal to 1 as a unit of 1. As a unit of 1. So examples of dimensionless unit are strain. Strain is change in length over original length. Change in length, the unit of length is meter. The unit of original length is meter. So the units cancel meter, you have 1. So that brings us back to 1 again. So it's dimensionless, but the unit is equal to 1. Specific gravity is another one. Specific gravity is density of a given fluid over density of water or standard fluid. So since they are both density at the numerator and density at the denominator, the unit will be the same, and the unit cancels out, you have 1. So again, the unit is 1. So dimensionless quantity are quantity that has a unit of 1 or has no physical units. Angle is another dimensionless quantity. So let's move to next slide. So here we are given question. We are asked to derive the dimensional formula of the following quantity and write down their dimensions. Derive their dimensional formula, that is in terms of m, l, t. And then write down their dimensions, that is the power to which the fundamental quantities are raised. So density, the formula for density is mass over volume. Mass over volume. So that gives us mass, capital M, volume, L raised to 3. There is no time in this. So by the time we bring them together, we have M, L, 3. If we decide to include T to make it complete, then T will be raised to 0. So m is raised to 1, L is raised to 3, T is raised to 0. So the dimensional formula for density is ML3. So what is the dimensions? The dimension will be 1 in mass minus 3. Sorry, this is minus 3. L raised to minus 3. 1 in mass minus 3 in length and 0 in time. 1 in mass minus 3 in length and 0 time. So that is the dimensional formula for density and the dimensions for density. Let's move on to the next example, which is power. What is power? The rate at which work is done. So power is work done over time. What is work done? Work done is force times distance. So force, which is M L T minus 2. Distance is L, then over T. So if we put them together neatly, we have M1, L2, T minus 2 minus 1, because this T at the denominator will go up and become minus 1. So that gives us minus 3. So the dimensions of power is 1 in mass, 2 in length, and minus 3 in time. One in mass, 2 in length, and minus 3 in time. And the dimensional formula is ml raised to 2t raised to minus 3. So that is the dimensional formula for power and the dimensions for power. So let's look at the next example. The next example is coefficient of viscosity. Coefficient of viscosity is given a formula: force times distance over area times velocity. Force as coefficient of viscosity is equal to force times distance over area times velocity. So now, if we write down the dimensional formula for all these parameters, we have force is M L T minus 2, distance is L, and then area is L2, velocity is L T minus 2, LT minus 1, LT minus 1. That is velocity. Because the velocity unit is meter per second. LT minus 1. So if we rearrange this formula properly, we'll have M This is 3, 2. So we are going to have 2 minus 1. That will be L minus 1. And then we have T minus 2 up, minus 1 down. If minus 1 down goes up, it becomes plus 1. So that will be T minus 1. So this is the dimensional formula for viscosity. And the dimensions for viscosity will be 1 in mass, minus 1 in length, and minus 1 in time. Minus 1 in time. Right. So finally, the last example is angle. In our previous slide, angle was mentioned as one of the examples of dimensionless quantity, which means it has a unit of 1, but no physical unit. So if it does not have physical unit, it means it is dimensionless. So we can write, if it is dimensionless, you can write that M is 0, L is 0, T is 0. So it has a unit of 1. So the dimension of angle is 0 in mass, 0 in length, and 0 in time. A unit of 1. So that is angle. Now we'll move on to this example 1. We'll go on to example 2. Example 2. Explain which of the following pair of physical quantities have the same dimension. Explain which of the following pair of physical quantities have the same dimension. So the first one is work and power. Does work and power have the same dimensions? That is the question we are asked. So let's look at it. Work, force times distance. Work is force times distance, and force is M. Force is M, L, T minus 2. Distance is L. So if you bring them together, you have M, L2, T minus 2. So this is formula for what happened? All right, so let's continue. So our work has a dimensional formula of m L2 T minus 2. We want to know if the dimensions of work and power are the same. So keep this in mind. Work is m L2 T minus 2. Now, power. What is power? Power is the rate at which work is done. So power is work done over time, which implies that we have a unit of work divided by T. Divided by T. So that will give, if we move this T up, that will give us M L2 T minus 3. So now we can see that power and work have different dimensional formula. So they are not the same. They don't have the same dimensions. Since they don't have the same dimensional formula, definitely they are not going to have the same dimensions. Now, the second example there is stress and pressure. So what is stress? Stress is force over area. And what is pressure? Pressure is force over area as well. So by definition, they are the same, which implies that they will have the same dimension. Since both are force over area, so it means that force, which is MLT minus 2 over L2. So that gives M L minus 1 T minus 2. So they are the same. The next is impulse and momentum. What is momentum? Mass times velocity. What is impulse? Force times time. So momentum, mass times velocity. Mass is m, velocity is L, T minus 1. Impulse is force times time. Impulse is force times time. That is, force is m, L, T minus 1. Time is T. Force minus 2, time is T. So force is MLT minus 2, time is T raised to 1. So if we take this indices, it will give us MLT minus 1. So impulse and momentum have the same dimensions. Impulse and momentum have the same dimensions. All right. So I will move to dimensional analysis. What is dimensional analysis? Dimensional analysis is the use of a set of units to establish the form of an equation, or more often to check that the answer to a calculation has a guard against many simple errors. We can also define dimensional analysis as a method of analysis in which physical quantities are expressed in terms of their fundamental dimensions that is often used when there is not enough information to set up precise equation. So with these two definitions, we can say that dimensional analysis helps us to check an equation if it is correct. It also helps us to formulate a new equation between parameters, how they are related. So what are the applications of dimensional analysis? One, to check the correctness of physical equation. To check the correctness of physical equation. Two, to derive the form of a physical equation. That is, you are given parameters and you know their relationship. Based on their relationship, you derive an equation, entirely new equation based on the information you have, how the parameters are related. And then to derive the relationship between different units or different systems of a physical quantities. Yes, previous class we talked about metric system, how we can convert from one metric system to the other. So dimensional analysis can also help us do that. Now, principle of homogeneity. It states that the dimensions of all the terms on both sides of an equation must be equal. Must be equal. So if we are given an equation, for the equation to be homogeneous, for the equation to be accepted, the terms on both sides of the equation must be the same. So according to this principle, the comparison, that is the equal sign that separates the left side of the equation from the right side of the equation. The addition, that is, we have parameters that we are adding together, and subtraction of all physical quantities is only possible if they are of the same dimensions. That is, for us to add two quantities or subtract two quantities or equate them, they must have the same dimensions. They must have the same dimensions. So let's look at the example there. A physical relation must be dimensionally homogeneous. All the terms on both sides of the equation must have the same dimension. In the equation, S is equal to UT plus half AT squared. Now, in this equation, you notice that S is on the left, ut plus half at squared. This equation is only correct if all the dimensions of each of the combination, that is the ut and at squared, are of the same dimension and is also equal to S. Now, S in this equation is distance or length. So let's analyze this. If S is length, it means that it will have a dimensional formula of L. Now, U is velocity, which is L t minus 1. U is multiplying a t, ut. So we add another t to it. So if we simplify this, this gives us, these two will cancel. This is t minus 1, t raised to minus 1 times t raised to 1. So that would be t raised to 0. Minus 1 plus 1 will be 0. Anything raised to 0 is 1. So ut will give us L as a dimension. Ut will give us L as a dimension. Remember, for S we have L, for ut we have L. Now, what of half at squared? Half at squared. A is length t minus 2, that is meter per second square. Then t square, which means the time is raised to 2 square. Now, if we take the indices of this common term, t, we have minus 2 plus 2 will give us t0 raised to 0. Again, t is raised to 0, which is 1, implying that we have only L left. So for S, we have L. For ut, we have L. And then for at squared, we have L. So on both sides, we have L only, representing their dimensional formula, which implies that this equation is a correct equation. The equation is correct and is homogeneous, and it must be accepted. So that is how to test if an equation is homogeneous or if an equation is correct. We must apply the rule which states that to compare, add, and subtract, what we have on both sides of the equation must be the same. They must have the same dimensions. We didn't mention multiplication and division. Remember, it's only addition, subtraction, and comparison. That is equation. To equate. So here is another example. We are given V is equal to U plus AT. V is equal to U plus AT, and we are asked to test or check if the equation is correct. So what is V? V is velocity. The unit of velocity is LT. The unit of velocity is LT raised to minus 1. Now, that is for V. Then for U, U is also velocity, which is initial velocity, the same unit, L T raised to minus 1. Now, the third parameter there is AT. A is LT raised to 2 minus 2, and T for T, time for T. So if we simplify this, here we have LT minus 2T1. So that would be minus 2 plus 1 will give us minus 1. So we are going to have LT minus 1. LT minus 1. So now, if we now compare the three-dimensional formula, you discover that what we have on both sides of the equation are the same. V, which is represented as LT raised to minus 1, U, which is represented as LT raised to minus 1, and then AT represented now as LT raised to minus 1. They are all the same. So it means that this equation is correct. Now, let's look at another example here. So what are the dimensions of A and B in the expression F equals A square root X plus B T squared, where F is force, X is distance, and T is time. So if we follow the principle of homogeneity, it simply implies that for this equation to be correct, all the parameters must have the same dimensions. So now we are going to split the equation. So in that case, it simply means that F is equal to this, and then F is also equal to this. So F is equal to A root X, and F is equal to BT squared. That is what it means. By dimension, they must be equal. So if we solve this mathematically, F, taking the first two terms, F is equal to A square root X. We are looking for A, which means that A will be equal to F over X square root. So which we can rewrite as A is equal to F over X raised to half. So now our F is this. Our F is MLT minus 2. Our F is MLT minus 2. While our X is distance becomes L raised to half. L raised to half. So if we rearrange our expression, we'll have M L T minus 2 dot L raised to minus half. So if we take like terms, that will be L1 minus half. 1 minus half is half. So we are going to have our expression A. Expression for A will be A is equal to M L raised to half T raised to minus 2. A is equal to M L raised to half T raised to minus 2. So that is our dimensions for A, dimensional formula for A. Now, how do we find B? Similar way we can find B. So B will be F. From this equation, it will be B is equal to F over T squared. So F is MLT minus 2 over T squared. So if they want T squared at the denominator is taken up, we have our expression to be MLT minus 2 T minus 2. So that will finally give us B as MLT minus 4. So that is the correct answer. So let's make progress with our class. So this is how to test if an equation is correct or not. Remember, it's one of the application of dimensional analysis. So now we will look at the second application of dimensional analysis, which is to derive the form of a physical equation. So, for instance, we are asked to find an expression for the time period of a simple pendulum, which depends on the length, mass of the bulb, and acceleration due to gravity. So in this equation, the time period depends on length, mass, and acceleration due to gravity, 3 quantities. The time period is depending on 3 quantities. So what mathematical equation can we derive to show how this time period depends on these 3 quantities? So we start with writing an expression such as T is proportional to L, which is length, raised to A, that is the power to which they are raised. Then M for mass of the bulb, the power to which it is raised, and acceleration due to gravity, C. Now, remember that we don't know how they are related. We just want to derive an equation to show actually how that is their true relationship, how they are truly related. So if I take up this proportional term, I will replace it with a constant. Remember that in in physics or mathematical science, parameters can be related directly or inversely. Parameters can be related directly or inversely, that is directly proportional or inversely proportional. So that we should have that at the back of our mind. Now with this, if we take off the proportionality sign, we'll have T to become K. Now in dimensional analysis, constant terms can be neglected, can be ignored. It does not really affect the solution of the problem. Constant terms can be ignored. But if you choose to retain it, there is no problem because it's a dimensionless constant. So you can ignore them. And also figures, numbers can also be ignored. Not the powers to which the fundamental quantities are raised. Just figure multiplying the values could be ignored. So we have L. This is length. So let's write our dimensional formula. L, A. This is mass. Let's write our dimensional formula, proper dimensional formula. MB. And then acceleration due to gravity. G. The unit is meter per second square, the same unit as acceleration. So that is L T minus 2, all in bracket raised to C, because G is raised to C. So now, like I said before, we can choose to ignore K while we are solving. Then when we are through, we can return it or we completely leave it. So let's continue with our solution. So on the left side, we have T, which is time. So we write the dimensional formula also for time. So that is T.
Hello, sir. We can't see us. We can't hear you anymore, sir. Sorry, sir. We can't hear you, sir.
Right. So now we have period T. The dimensional formula is T and it's raised to 1. Then we have M raised to B, L raised to A, L raised to minus 2C, and T raised to minus 2C. Based on what we've done before, T is raised to minus 2C. So if we simplify this expression, we are going to have T raised to 1, M raised to B, L raised to A plus, sorry, A minus A minus 2C, and then T minus 2C. A minus 2C. A minus C, not A minus 2C. A minus C. A minus C. No, A plus C. Because we have L, T minus 2 in bracket C. That is our G. So it's going to be L, A, L, C, and T minus 2C. That's what we should have. So correct yourself. Now, so we are going to compare what we have on the right and what we have on the left. On the right, there is no M. There is no M, so B will be equal to 0. Since there is nothing here, there is no M represented here, it means that B is equal to have L raised to A plus C. So we say that A plus C is equal to 0. And then T on the right, T is raised to 1. On the left, sorry, on the left, T is raised to 1. On the right, T is raised to minus 2C. So now with this information we have generated from the equation, we know that B is equal to 0. C will be equal to minus 1 over 2. That is from this. So if C is equal to minus 1 over 2, then from this, we substitute C as minus 1 over 2. If we do that, it implies that A will be equal to 1 over 2. Here, A will be equal to 1 over 2 because C is minus 1 over 2. If we substitute C as minus 1 over 2 here, A becomes 1 over 2. So now we have our dimensions for the expression given to us for A, B, and C. B is 0, B is 0, A is 1 over 2, C is minus 1 over 2. So if we come back to this expression and substitute in the dimensions, we are going to have T is equal to K L is raised to B, which is 0. Sorry, L is raised to A, which is half, raised to half. Then M is raised to A. M is raised to B, which is 0. B is 0. And then C is raised to G is raised to C, which is minus half. So I take it again. Coming to this equation, we have T is equal to K, L, A, M, B, G, C. So if we substitute the parameters, T is equal to K, L raised to A, which is half, L raised to half, M is raised to B, which is 0, M raised to 0, and G is raised to C, which is minus half. So now, if we now rewrite this in proper context, our T becomes K square root L over G. M is raised to 0, which is equal to 1. So M will not appear in the expression, which simply means that the period of the simple pendulum depends on the square root of the length of the thread used and the inverse square root of the acceleration due to gravity. So this is a correct representation of how the period is affected by the length, the mass, and the acceleration. So in this expression, it shows that the mass of the bulb does not affect the period of the simple pendulum. So this can be also interpreted as, if I have a ball, simple pendulum ball of different sizes, let's say 10 gram, 15 gram, 20 gram, 50 gram, I should have the same period because the masses will not affect them. For the number of oscillations, I should have the same period because the masses, the different masses will not affect the period of the simple pendulum. So take note of that. So we move on to let's look at this. So here we are given when mass is converted into energy, let the energy produced depend on the mass and speed of light. So this is Einstein mass energy relation. So we are asked to show how energy is dependent on mass and the speed of light. How energy is dependent on mass and the speed of light. So to do this, we will start from the first principle, which is energy. We say is proportional to mass A and speed B. So energy is equal to K M A C B. It's A and B that we want to find to know how they are actually related. So dimensional formula for energy. Dimensional formula for energy is M L2 T minus 2. ML2 T minus 2. It has the same dimensional formula with work done. Energy and work done have the same dimensional formula. So now, what is M? M is mass. So that is capital M A. What is C? C is speed of light. So the unit of speed is length per time, all in C. So let's write our expression with the space we have. So we have M L2 T minus 2 is equal to M A L T minus 1 all raised to B. So if I open up this bracket, I will have M A L B T minus B. So if I compare term by term, on the left side, I have M raised to 1, which means that A is equal to 1. On the left side, I have L. L on the left side is raised to 2. On the left side is raised to, on the right side, it is raised to B. So which means that B is 2. And then for T, on the left side, I have minus 2. On the right side, I have minus B. So minus strikes out, B remains 2. So if I come back to original equation where I have E is equal to K M A C B and substitute the values, I will have E is equal to K M C 2. A is 1, C is 2. So this is Einstein energy formula that we know. If we say that K is a dimensional quantity, constant, and is equal to 1, then we can rewrite our expression firmly as E is equal to mc squared. mc squared. So that is how to derive an equation from relationship between physical quantities, from parameters. So that is by application of dimensional analysis. So now the third application of dimensional analysis is to convert from one system of units to another. To convert from one system of units to another. Now, this has a general rule or formula. Remember that physical quantities are represented in two parts. That is, when measurement is done, it has a numeric part and alphabetical part. So let's represent the numeric part with n, and the alphabetical part, which is the unit, with a u. So n stands for numeric part, which is the size, the amount, the magnitude, while the u stands for the units that specify the quantity measured. Now, this unit u is what we have represented in dimensional formula as MLT. MLT. So if I'm given a problem in one system of unit and I'm asked to convert to another system of units using dimensional analysis formula, I can write that N1 U1 is equal to N2 U2. So assuming I am given this and I'm asked to find this, I'm asked to find this. So by rearrangement, N2 will be equal to N2 will be equal to N1 U1 over U2. N1 U1 over U2. So that is how we can rearrange to find N2. So now, but our U, which is the unit, in dimensional formula is MLT. So the MLT will take the nomenclature 1 for the numerator and then 2 for the denominator. So that is how this formula came about. So N2 is equal to N1 and bracket M1 over M2, then to the powers to which they are raised. Remember, you must know the power to which they are raised. You must know the power to which they are raised. So we have N2 is equal to N1 in bracket M1 over M2 bracket close raised to A. Then L1, L2 in bracket raised to B, and T1 over T2 in bracket raised to C. So we have raised to A, B, C. Raised to A, B, C. So if you follow the guide, the method to go about the conversion, the first one is write down the formula. The second is find the values of N1, that is the numeric value given in the question, and values of A, B, and C. A, B, and C are the units. That is the power to which the units are raised. For instance, if I have a unit of meter per second square, it means that M has a unit of 1, S has a unit of 2. So if M is A, it will be 1. If S is B, it will be 2. So, but here, in this case, this is L T minus 2. So L will be raised to B, which is 1. T will be raised to C, which is minus 2, regarding this illustration I've given. So the next thing to do is substitute the values of L1, M1, L1, T2, that is the given value. This given value are the units. For instance, if I'm given 5 kilogram meter per second square, 5 kilogram meter per second square, which is a force unit. Force is mass times acceleration. Mass kilogram, acceleration is meter per second square. So in this value, 5 is my N1. N1 is equal to 5. M is equal to kg. L is equal to M. T is equal to S. Now, kg is raised to 1, so which means that L, B, C. A will be equal to 1. L will be equal to 1. And then T will be equal to minus 2. T will be equal to minus 2. Because if I write this, I will have 5 kg M S minus 2. So now you know what A is, what B is, what C is. What B is, what C is. So you substitute them into this formula. Now, if I'm to convert 5 kg meter per second square into a lower unit, like to gram centimeter per second square, that is gram centimeter per second square. Kilogram meter per second square to gram centimeter per second square. So my M1 is kg, M2 is G, L1 is M, L2 is cm, T1 is S, T2 is S. That is how to solve it. Then we'll now solve for the number N2. So what will the number be? So we'll solve an example to buttress the explanation. So here is an example. The question says the density of mercury is 15 gram centimeter per cube, or 15 gram per centimeter cube in CGS. CGS simply means that is a metric system. Centimeter, gram, second. That is what CGS stands for. Now we are asked to find its value in SI unit, that is standard form. Standard form is always MKS, that is kilogram meter second, MKS. So now we have to identify our parameter. The first step, remember, is to write down the formula. N1 is equal to 15. Then A, that is the power to which the mass, that is gram, is raised to is 1. So A is equal to 1. Length, Cm, is raised to -3. So B is equal to -3. There is no time given in this equation. There is no time, there is no second there. So the time factor C is considered 0. So now coming down to point 3, which is put values of M1, L1, and T1 in the system given in the equation. What is our M1? M1 is in gram, L1 is in cm, T1 is not given. There is no time. Now, the new system, which is the one we are converting to, MKS, will be M2, L2, and T2. So M2 is kilogram, L2 is meter, because we are converting from grams per cm cube to kilogram per meter cube. So now we have been able to identify all the parameters given. The next step is to put all the values in the formula we have in step 1. The formula we have in step 1. So 15 for N1, we substitute that. 15 for N1, we substitute that. Then gram for M1, kg for M2, cm for L1, meter for L2. And T, there is no T. So we just leave it as it is. Now, don't forget the powers to which they are raised. The powers to which they are raised. A is 1, B is -3. So we raise them accordingly. And since there is no C, C is considered to be 0. And so if we put 0 there, it completely makes the T1 over T2 to become 1. Because anything raised to 0 is equal to 1. And whatever you multiply by 1 is that same value. So the T on its own will fizzle out because it's raised to 0. Now, since we are converting to kilogram, it means that we have to convert gram, we have to write the gram in kilogram. So 1 gram into kilogram will be 1 divided by 1,000. If I want to convert 1 gram to kilogram, I will have to divide it by 1,000. So we have 10 raised to -3 there. Then if I want to convert cm to meter, I'll have to divide by 100. And that is 10 raised to -2. So if I open up the bracket, I will here 10 raised to -3 is also raised to 1. So -1 times 1 is -3. So here our -10 raised to -3 will remain. But in this case, we have 10 raised to -2 in bracket raised to -3. So -2 times minus 3 will give us 6. So here we are going to have 10 raised to 6. That is in this part. We are going to have 10 raised to 6. So now, if we bring out everything here, we have 15, 10 raised to minus 3 times 10 raised to 6. So 10 raised to minus 3 plus 6 will give us plus 3. 10 minus 3 times 10 6 will be 10 minus 3 plus 6. So that will give us 10 raised to 6. I mean, 10 raised to 3. So now we'll be left with only, because we have resolved this, we have taken care of 10 raised to 3 and 10 raised to 6, which gives us 10 raised to 3. So we have 15 times 10 raised to 3. We have 15 times 10 raised to 3. Then the unit comes kilogram, meter raised to cube. So this is how to convert using a dimensional formula. This is how to convert from one system of units to another system of units. So this will be the end of the class. So you can always go back to the YouTube and go through the teaching. Ensure that you
Sir,
subscribe. Yes.
yes, sir. Sir, please, can we have the slide, please?
The slide.
Yes, sir.
Everything is there now. Okay. All right. No problem.
Thank you, sir.
All right.
So our next class is when, sir?
And that will be next week.
Okay, sir. All right, sir. Thank you, sir.
Okay.